In this video, we're going to use Gauss's lemma to prove that if you have a polynomial with integer coefficients that's reducible over q, meaning you could factor f into two smaller polynomials with rational coefficients, then you didn't really need rational coefficients after all. It's really reducible over the integers. So let's do an example before we prove this. So for example, I could take 8x squared plus 2x minus 1. That's a polynomial with integer coefficients, and you could factor it over q. I could write this as 8x plus 4 times x minus 1/4. And if you distribute, you could see you get this polynomial back. So I used rational coefficients, but I didn't really need to. If you look at this, I can take the first parentheses and factor out a 4. This first polynomial is not primitive. I could factor a coefficient out of every, I could factor a common term out of every coefficient. So I can get 4 times 2x plus 1. And in this polynomial, I can factor out a 1/4. I could factor out a 1/4 and write that as 1/4 times 4x plus 1, or 4x minus 1. This 4 and this 1/4 magically cancel, and I'm left with 2x plus 1 times 4x minus 1. Now I have integer coefficients. So the theorem says this can always work out that way. If you could factor over q, then it turns out you could really factor over z. So I'm going to prove this. I'm going to start by saying, without loss of generality, I'm going to assume f is primitive. How can I assume that? Well, if my function f was not primitive, if I could factor out a constant, so if I had a constant times my polynomial, I factored out something in every coefficient, and if that could be factored over the rationals, so maybe I could write this as f of x equals g of x times h of x, where g and h are over q, then I could just divide both sides by c, and I could write this as f of x is 1 over c g of x times h of x, and still both these polynomials have coefficients in the rationals. So I might as well assume that f is primitive to begin with. So I'm going to assume that for this proof, and I'm going to suppose that f of x is g of x times h of x, where g of x and h of x are in the polynomial ring with rational coefficients. So g of x, h of x in this polynomial ring. Now I'm going to take a and b rational numbers such that a times g of x and b times h of x have integer coefficients and are primitive. So I'm going to find numbers that I can multiply by g and h to get me integers, and I also want to multiply by the correct constant to get primitive polynomials. So let me give you an example mid-proof of what I'm talking about here. So if maybe g of x is equal to 1/3 x squared plus 2/5 x plus 1, I need to multiply by some constant to basically clear all the fractions, but I don't want to multiply by anything more than necessary. So I'm going to take a to be 15. Because if I multiply this polynomial by 15, I'll get 5x squared plus 2x, plus 6x plus 15, and the coefficients are then relatively prime. See, I wouldn't want to multiply by 30 or something, because then my a is too big and I don't get a primitive polynomial. If, for example, h of x was already an integer, maybe, let's say h of x was 6x squared plus 18, then I'm going to take b to be 1/6, and I'm going to divide by the common divisor. So hopefully these examples make it clear that I can always find an a and a b to multiply by my polynomials to get integer coefficients and so that my polynomials are primitive. So then what happens? I could take my relationship between f, g, and h and multiply both sides by ab. So abf is equal to a times g of x times b times h of x. So I multiply both sides by ab. Both of these polynomials are now primitive. And by Gauss's lemma, when I multiply two primitive polynomials, I get back a primitive polynomial. So this is primitive. It's a primitive polynomial. F itself is primitive. That means the greatest common divisor of the coefficients of f is 1. And I'm taking every coefficient in f and multiplying by the constant a times b. So the greatest common divisor of the coefficients in ab f of x is ab. However, ab f of x is primitive. This implies that a times b has to be equal to 1. It's just kind of like what happened in our example up here. The 4 and the 1/4 multiplied gave me 1. That happens every time is what I'm showing you. If you started off with a primitive polynomial and you do this, the a times b gives you 1. That means f of x, a times b is equal to 1, is equal to a g of x times b h of x, and both of these are polynomials with integer coefficients. So I'm done. That is the proof of the theorem. If I start with reducible over Q, it's really reducible over Z.